Thank you. So, yeah, that is a little bit about me. Let me tell you about my facility, and let's see how I braved a video, and we're going to see if I regret this. If not, then I will talk for a while, but I think the video will be on a little bit of a delay. So a little bit about the Linac coherent light source. If you're not familiar with what a light source is, it is a thing that generates light, specifically X-rays. The way we generate ours is a little bit different from the synchrotrons you might be familiar with. We generate our light using the linear accelerator, which is this 2-mile long building that goes under 280. We generate the electrons at one end. We spin them up to 99.999% the speed of light. Then we send them through a bunch of magnets at the end and wiggle them back and forth. And it turns out when you wiggle those magnets back and forth, we generate these coherent pulses of X-rays. We then send those X-rays further down the line in electrons. We unceremoniously dump the electrons for science and let the photons pass through, the X-rays pass through until they interact with our sample. In the experiment halls, we have 7 to 10 instruments, depending on how you count. The X-rays hit the sample, they diffract, they scatter off of it, and the scattered photons hit an X-ray detector. My data system captures those pulses and then sends them to a data center where they're processed and analyzed, and we learn exactly where those atoms and molecules are and where they are in relation to each other and how they move in relation to each other as a function of time. So that is, in a microcosm, the lightning summary of what an X-ray laser does and how it works. It tells you at a molecular and atomic level where your atoms are and how they move relative to each other as a function of time, and lets you make movies of exciting things like across a wide variety of fields. So we can do chemistry, we can do catalysis, coincidence spectroscopy, coherent imaging, spectroscopy, crystallography. So you can throw a protein in there and understand, your COVID. You can take a picture of your COVID molecule and see where all the bits and pieces are on the crown. You can watch chemistry happen. You can watch bubbles forming on an anode or cathode. So it's a wide variety of experiments. We have hundreds of users per year and roughly 20 experimental techniques in play across these instruments. And all of them have different workflows, and all of them have different data requirements and different compute needs, which makes this a very challenging environment to work in. So in order to get a sense of how much computing we're going to need in the future, we had to, this is the one on the delay, I should be watching that one. We had to figure out, how much data are we going to be producing in the near future? So in case you're not aware, you mentioned LCLS-II. So currently, we're in the midst of an upgrade. And previously, we were getting X-ray pulses at the rate of 100 per second, 120 per second. So about 120 times per second, we get an X-ray pulse come down the line, take an image, it destroys, vaporizes the sample. These X-rays are super bright, so they burn through everything. They vaporize the sample, but before they destroy the sample, they diffract and they hit that image, and you can get a picture of what that molecule looked like shortly before you vaporized it. So each shot is an experiment, okay? So each shot is important. Each 120, frame, each frame that comes out is important. And now we're going from 120 to 1 million per second. So the LCLS-II upgrade increases that repetition rate of a laser from about 100 per second to 1 million per second. That's a lot of data. And so that's a huge increase in the data rate. We do work a little bit smarter, and we do put some data reduction in between, us and the disk, or the source and the disk. So there's a slight reduction in the data rate, but by the time we were writing to disk, we're writing 20 to 100 gigabytes per second to disk. So it's quite intense. We're expecting to see about 100 petabytes per year in the first year once we really crank it up. I should point out, y'all, this is a log plot. So this is what we expect our data output to be with data reduction blue line over time. So this is hard. If you look at the computing challenges, it gets worse. We aggregated all of these different workflows and we benchmarked them all. And we said, okay, assuming that we're processing at 120 times a second now, And we can keep up using, say, 10 computers. How much are we going to need when we go to 1,000,000 times a second? And the answer was to about 10,000 times more computers. And we went, that's a problem. we have neither the power, space, computing budget, or anything on site to handle that much data. What are we going to do? So fortunately, what we found is that most of the experiments sit into this lower bin right here, which fits into our local data center, the SLAC Shared Science Data Facility, the S3DF. And those local resources are sufficient to cover about 80% of the experiments. So good news there, 80% of the experiments are covered by this. However, if we want to study photosynthesis in action, which is something we very much like to do, it's up there, okay? Now I require exascale compute. This is basically, I need an exaflop to analyze this data in anything approaching a reasonable time scale. This is, as they say in kids' shows, a super big problem. So how are we going to solve this? So luckily, even though we ourselves do not have a supercomputer on site, we have an okay computer, it's mid-scale, but we have one right across the way. We have NERSC. So we said, help us. And NERSC came to the rescue. So the plan is 80% of our experiments run at SLAC. 20% get surged out to NERSC, and everybody's happy because everybody gets to do their research. Now, this is where the problems begin. How do you do that at an efficient scale? So in a typical experiment, I should point out, just so you know what it's like, every 5 days, I get new experiments. I have 2 or 3 running at once. So we're a little different from the synchrotrons, which have 100 running at once, but I have 3 experiments running at once, not so bad, but they're all producing, 20 to 100 gigabytes per second, so not great. They have 12-hour shifts, so there's a day shift and a night shift. And on any given week, I might have an experiment that only requires about a petaflop and can analyze their data on the laptop. Or I might have 3 experiments that are running that all require basically, a large data farm in order to analyze their data. And I don't know ahead of time what I'm going to get. I mean, we have allocations, people submit proposals, those get ranked, the highest ranking proposals get beam time, and then that beam time gets allocated. So I know about 8 or 9 months in advance, roughly how much computing is going to be required to analyze in particular week. In addition, those experimenters need to be able to know what's happening in their experiment while they're doing their experiment. So they do need to be able to get very fast feedback to know that, I've just moved a motor, let's see what happened. They need to be able to get feedback about their data quality to understand, are they resolving the structure? Is there signal to noise what they expect? Have they found the peaks where they're supposed to be? Is the detector focus correct? So lots of information that they need to gather that they need to see roughly live. During the off shifts, they often process all of the data they've taken that day and make decisions about what they're going to do on the next day during their next shift. Beam time is at a premium, so they have to make the best use of the time when they're both on and off shift to understand what's happening in the experiment and how to answer the most science questions with the time that they have left. When they go home, most of their data stays at SLAC on the S3DF. And for the 4 months following the experiment, they can analyze their data. And then it does also get archived to tape where it stays for 10 years. And they can restore it at any time and use it on disk. We say 4 months because we've noticed that after about 4 months, people stop touching their files. So we know that either a publication comes out in 4 months or people give up. We're hoping, we think it's a publication. So, but that's where the 4-month policy came from. It's actually, it arose through study, not arbitrary choice. You can take longer to analyze. If you're a user out there, if you want to take longer to analyze your data, you feel free. We will keep it on disk for you. But that is roughly what our work pattern looks like. And you'll notice it's very bursty, and it doesn't usually fit the standard pattern for a compute farm. So the first problem we decided to solve, and we asked NERSC to help us solve it, was single particle imaging. And this is one of these canonical experiments where you're throwing a sample randomly oriented into a beam of X-rays, scattering and capturing an image. You do some data reduction on it before it gets to the farm. The farm has to do all of the reconstruction, the reconstruction. So it's a hugely compute intensive workflow for us. And they applied there. And I felt like you should be able to see what some of these instruments look like. So some people have these beautiful telescopes at the top of the mountain, and I love those. Mine are all underground layers that look like evil scientists put them together with wires and like tinfoil hats all over the place. It's great. But it's a beautiful thing, and it's amazing. Given, this is amazing. The amount of science that can come out of this is beautiful. So I wanted to make sure that you all can see what the instruments actually look like that we're capturing some of this data. So back to ExaFEL. So ExaFEL was the project that was defined to tackle this single particle imaging problem. And it was an ECP project. And it dealt with three aspects. And these three aspects of the problem were repression. So it wasn't that we just said, we just need to access NERSC and then everything's going to be fine. Or we can just parallelize our way out of it and it'll be fine. Or we'll just be smarter about how we analyze the data and make it more efficient. We'll work smarter and it'll be fine. Nope, we said we're doing all three. And we partnered with NERSC, we partnered with Oscar, we partnered with people in computer science, and we addressed all three aspects of it to handle every aspect from the data flow, from the SLAC side to the NERSC side, the network orchestration, the workflow orchestration, getting it into the computer, because edge to edge is kind of easy. Getting out of my facility and into your facility is where things always get hard. Figured out that problem. Being able to launch on hundreds of thousands of cores at once, also difficult. Figured out how to scale the software. And at the end of the day, we built this. So we built this workflow that basically streams the data over to NERSC, comes in. We have some automated data processing. So as soon as we start a run, we start acquiring data. That's a trigger for our system that says, tell the super facility API, data's coming, expect it here, start a job as soon as it gets there. And then we can start our jobs, watch the results come back, send those results back to SLAC, where the users can interact with them and view them in real time. So this achieved these analysis results within minutes, which is what we were looking for. And it was a great pattern where it was a success. We were able to reconstruct several structures. And then internally within SLAC, we were able to implement our version of the super facility API so that now any experiment that comes in to any instrument at LCLS, whether it's running LCLS-I, LCLS-II, high rate, low rate, whatever, can have access to NERSC resources in real time. Now, I will say for the moment, it's still reservation based. So if you say you need NERSC, tell us ahead of time you want to use NERSC, we check a box, we make sure that that everybody's okay with that, we make a reservation, we use it. So this is in use. It's a fantastic tool. I would be remiss if I didn't say that there were, whoops. Did I hit it too many times? Okay, no. Okay. I'd be remiss here if I did not say that there are other experiments also at SLAC, also using, this is not a light source. This is LZ, this is Lux Zeppelin, this is from Maria Elena. And they're doing a dark matter search underground. And it's a beautiful thing. It's got these photomultiplier tubes, big bucket of liquid xenon, and they're just waiting for dark matter to come in and bump into one of those little xenon things, and then create a little pulse of light that they can see in these photomultipliers. And for that, they're trying to analyze these billions of events per year, and NERSC provides all of the prompt processing, the long-term archive, and the computing that provides introspection into the data. So I wanted to point out that the collaboration between SLAC and NERSC is broader than just LCLS. Even though I'm sitting here talking about the LCLS part of it, it also extends to other experiments. So I kind of wanted to take the second part of the talk and talk a little bit about where I see the future relationship going. And so I think we've established that LCLS and SLAC in general have extreme computing needs that do require the use of offsite HPC compute. And it turns out real-time analytics, which this previous use case was based on, is not the only use case. We have lots of real-time, time-sensitive, but also data-intensive workflows that we need. In addition to that, since we started working on this, ML has come on the scene, computers have become a little more programmable and more accessible. And it's just exploded the desire for people to do almost anything and everything with machine learning. So we have, I would say, unbounded aspirations for AI-powered analysis. Technology itself is evolving rapidly, and so we need more algorithmic improvements, more newer hardware targeted to doing the kinds of science and the kinds of workflows that we're doing, and we need to adopt them. So good news is that right now, DOE is investing in infrastructure and programs to accelerate that scientific discovery. So there's HPDF on IRI, and there's FAST on the horizon. And I view LCLS NERSC partnership as a model for how you can use this local and remote HPC resources to do science, to accelerate science. So what's next for LCLS? What are some of the workflows and things that we're working on? So one thing that we've done is we've built this local data center. This is my OK computer, where that acts as a landing pad for all of my data. So there's all of this stuff happening under the hood to get the data into the compute center. And then that is my gateway to ESNet and to the other leadership class facilities. And SLAC is taking a very integrated approach to that. And LCLS is taking an integrated approach to that. So we are working with the other 5 light sources to try and come up with an interface that kind of matches this model of, this is what we have in common. And here's where we'll meet you. We can talk to the leadership class facilities with one voice and submit jobs and do things there. One thing I will say is I want to point out, you all know this, but the speed of light is constant. And it's a thing. It's a foot per nanosecond. And between LCLS and NERSC, there are, I'm hoping I get the number right, about in round trip, 400 microseconds. So in my brain, that's 400 pulses of the X-ray laser that go by minimum before I can get a round trip signal to my data center and back. Add in processing time, opportunity to launch jobs, waiting in a queue, and that becomes a very large amount of delay. So if I want to do any experiment steering, any direct control of the experiment, I'm going to do that locally, because there I have a few tens to 100 of microseconds of delay. And a little more control over my queues. So most of that is going to happen internally. And the stuff that needs more computing or needs a longer latency will go outside in my facility and will operate there. And to get to JLab and back is 26,000 pulses. So this is just for perspective here. I'm going to think local. No, I'm going to work local and think global. So I'm going to do most things locally, as much as I can locally within my needs, and only expand out when I need to and try to do so responsibly. So what's next? AI/ML is next. People are developing lots of machine learning algorithms in the offline. As you noticed, I have a need for experiment steering. So I'm going to try and move that online as much as possible. And in order to do that, I have several layers of online I can move to. I have basics in the detector that I can control. I have FPGAs in the detector that I can also program. I have FPGAs in my data reduction pipeline, which is my first layer of computing. That's the online layer. I have CPU and GPU there. And then only then do I hit disk. So, and then after that, I have more and more computing as available to me as I go out. But the upshot is that I need to have a method for moving things from the offline to the online, going from a model that can be millions of parameters large to fitting into an FPGA, which has a few tens of thousands of parameters. So to a itty-bitty living space. So that's one way we're trying to push, is to move things online. Another is to try and integrate as much as possible with the other light sources and seize the means of data production. So this is, we're trying to provide experiment steering infrastructure for the light sources as a whole. Not only that, but really that experiment steering infrastructure covers a lot of sins here. So it's dealing with not just the direct control of the beam or the direct control of the experiment, where you want a response within seconds or a minute. It's also dealing with these decision-making algorithms. So sometimes you want to know, have I accumulated enough data to move on to the next data point? Have I explored the phase space adequately? These are questions that require a significant analysis of data in order to answer, right? So you need more time and more compute in order to answer those. So these slower loops are ones where we might potentially involve the leadership class facilities in the future. And so the goal is to create some form of API between us, the light sources, and those leadership class facilities that's uniform enough that we can routinely make use of those external resources. So we're trying to close that loop between fast analysis, machine-assisted decision-making, data acquisition, and make it hum. So this is a complex slide, but the other side of what's next is in terms of experiment steering, I want to say is could be very simple, as in just controlling one point and then you need to analyze one piece of data, get feature extracted data and decide where to go next. But it could be quite complex. Could include developing a surrogate model that developing analysis that's fast, so taking analysis, taking a surrogate model, getting predictions from both at the same time, putting them together, synthesizing that information, making a prediction about where to go, and then directing the machine to do something. And in that case, you really are requiring a lot of computing, requiring at least 2 or 3 significant workflows that come together at the same time in order to drive the experiment. So it gets quite complex. So I wanted to introduce that idea before launching into digital twins, because here digital twins really are bidirectional information flow between the experiment and the model and so it's a bidirectional flow between the instrument and the compute. And you have at least 2 paths. You know, you have the experiment path where you're doing an experiment analysis. You have the surrogate model. Those may be reacting to each other. And then you have something to decide on how to direct the thing. So all of this combines a lot of compute elements together into one big happy package. But the promise is that you could really accelerate science if you could decode these structures in real time. You can understand what is happening in real time in a moving system like a chemistry system. So these sorts of models are have a high payoff if we can get them to work. So in addition, we are also sort of expanding outward. So in terms of machine learning, we learned that we need to be able to build large models. And so for that, we also do not fit into our data center. So we've tried to stream some of our data out to Oak Ridge and do some training there for the models that are just too big. We also, if we have models that are living at the edge that need to respond to experiment conditions. So our experiments are living, breathing things. Our buildings breathe, literally. When the sun hits the side of the building expands. And this changes the geometry of the instrument. And our models, turns out, are sensitive to that. So you have to be able to adapt to the sun warming the building, even though you're underground. And so all of these things kind of play into it. So you need a way to rapidly retrain. So not just train a large model, but also retrain and refine your model in real time in reaction to the data that's coming in. And so we've developed an infrastructure to do that with our Argonne friends. And so now, what I've described are these one-on-one LCLS to LCF or LCLS to a single light source collaborations. But instead of that could go one to many or many to many. So many light sources to many leadership class facilities. And that is sort of the idea of the Lumen and HPDF and IRI and all of these things. We're trying to bring that together and make that work. So a quick foray into what I view as the future opportunities. And this is now coming from a light source applications person, not, I'm sorry, there are no future opportunities. Our future is dead. No. And so one is the infrastructure. So the HPDF IRI, which have been mentioned, I think, repeatedly, are 2 programs that project and a program that I think are very important to the future of the light sources. I think NERSC's leadership in empowering the experimental facilities, allowing us, permitting us, enabling us to run at high rate at NERSC has really enabled this next leap into the future. And this is that look, this going from parallel play to integrated play, right? This is going from this one-to-one to the many to many. And it's a beautiful thing. I'm looking forward to it myself. And, just pointing out, SLAC really does have a lot at stake in this because, we have a lot of these time intensive and data intensive workflows along the bottom that all these projects that are kind of trying to take advantage of some aspect of the greater DOE ecosystem. So we are very much looking forward to that. And, before there was IRI, the light sources kind of sketched out, what it was that we would like if we had everything in the world that our little hearts desired to help our users do their science. What would we build? And so we kind of sketched a little picture where we said, well, we need help. We need to do experiment steering. So we need some scalable libraries. We need to store the data. So we need storage. We need to be able to do multimodal analysis. So we need to be able to move data from facility to facility, from facility to compute. So we need network improvements. We need discoverable data repositories. We need the ability to see where the data is, what it was, what the metadata is that's associated with it, under what conditions was it taken. And we need to be able to put all of that together, get seamless access to compute, and make it hum, in less than 3 to 5 years. So that was kind of our what's lovely to see is how much of that is now, at least becoming real, a part of the picture in HPDF and IRI. Our little heart's desires can come true. Christmas does come every once in a while. So other ways in which, I'm kind of looking forward to the future. So there's the CHIPS Act. There's been a lot of investment in AI. So I'm hoping that will let me drive my algorithms into the edge to make them efficient. It will help me with network and computing bandwidth and online. It will help me do experiment steering. So Linac is the big unifying piece that sits there in the middle between my instrument and facility and the leadership class facilities. So it's a way of connecting to the other light sources and connecting to the leadership class facilities. I think FAST is going to increase the use of AI and ML in all aspects across all facilities. And that's just like our compute needs are going to grow. So as much as I need computing now, it's getting worse and so much worse. And then, that new infrastructure that's offered by HPDF and that will come with IRI is going to be tremendously powerful and enable world-class science. So I will sort of end here and just say that, I think NERSC and LCLS together here are kind of synergistically driving to this new era of data generation on the one side and AI-based analysis and computing, computer science research, edge data processing, and making a merger of all of those pieces in one beautiful whole. And these are just my strategies for dealing with large data. And the first is find yourself a good partner that will let you connect to that computing seamlessly, easily. Keep that edge to exascale in mind. Remember that the speed of light is a constant, and do as much locally as you can. Do more with less data because all data are equal, but some data are more equal than others. It's not all information. Get for the information, save the information, toss the rest. Keep up with the rate of data production, scaling helps with that, and work smarter. And the last thing I wanted to make a pitch for is to say that the next big problem that I see looming is managing these data sets, because it's a lot of data. Our data is a national resource. We're going to be using it to train models and to build newer, better, smarter facilities. We're going to link our facilities and our leadership class facilities, experimental and observational facilities, and our leadership class facilities, and make smart instruments. So the data is the key component in that. So, I'm in. Thank you.
How do you handle the security issues of multiple users accessing common resources, running different codes at different locations, federated identity, blah, 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 discuss?
Yeah, badly. No, I would say with some with growing difficulty, maybe. So every user that comes to us has an account. Every user that wants to use NERSC has a NERSC account. Every user that wants to use Oak Ridge has an Oak Ridge account. Every user that wants to use APS has an APS account. You get the picture. So we have a bazillion accounts. They're all different. Same user, all different accounts. So that's the first problem. I only have to worry about the NERSC side and the LCLS side, right? So once they come in, they have access to our compute facilities and our data facilities. So, so at least from the perspective of taking data, acquiring it, and doing sort of the prompt analysis at the local data center, you know, there is an onboarding system, a way of bringing in a user, giving them an account, letting them do their thing. We have an automated run processing engine. So the code is written on top of a platform, on top of a stack. They plug in their Python, which has the science domain knowledge kind of encapsulated in it, and then run things on the farm. It is largely, but I mean, it's an enclave, right? That S3DF is an enclave, it's closed. And they run on that farm. They are vetted users. So in that sense, I think there is no security issue, although, you know, the code, of course, is written by users. So your farm needs to be about 10 times bigger than you think. This is not the fault of users. You stop once you get to the answer, right? You don't keep developing the code after that. It's good enough. You're done. When you want to go to NERSC, it's another problem. So to transfer the data, we do that through our, we do that locally through our account. So we transfer the data on their behalf. And then once it gets to the other side, we communicate what the permissions are on the directories. So, the user is associated with a repo, it's associated with an experiment, and that is, we transmit that information to NERSC. It is applied, POSIX, it's applied, the ACLs are applied on the far end, but they're communicated, asynchronously. So it's not like you can mirror the permissions we have on our data farm to NERSC. That's work. There was work to make that work, I would say. It's not seamless. It's not easy, but we try and keep it hidden, but it's a global issue. So they spawn jobs under their account. Johannes knows. There, yeah. Thank you.